Google's Cloud Spanner processes over 1 billion transactions per second. 90% of database outages are due to human error. Here's what most engineers get wrong when designing replication strategies. They don't fully grasp the trade-offs between consistency, availability, and partition tolerance. Remember this, we'll see why handling that transaction volume matters when we discuss scaling. By the end of this video, you'll know exactly how to choose the right replication method for any system, avoiding costly downtime and ensuring data consistency.
Let's define the scope of our replication strategy. Functionally, we need to replicate data across multiple nodes to ensure data is available even if some nodes fail. Non-functionally, we'll aim for high availability, durability, and low latency. Key clarifying questions include, what's the read-write ratio? What's the acceptable latency for reads and writes? What consistency level do we need? Are we optimizing for reads or writes? These answers will drive our replication strategy. We'll assume a 10-to-1 read-write ratio and a need for eventual consistency for most data, with strong consistency for critical user data like financial transactions. A critical requirement is idempotency, meaning operations can be retried without unintended side effects, especially important in distributed systems. Idempotency ensures that even if a write request is sent multiple times due to network issues, the data remains consistent. Now, let's move on to estimation. Let's say we have 10 million daily active users, each generating 10 write requests and 100 read requests per day. That's 100 million writes and 1 billion reads daily. That translates to roughly 11,500 writes per second and 115,000 reads per second. Assuming each write is 1 kilobyte, that's 100 gigabytes of new data per day. With a 3x replication factor, we need 300 gigabytes daily storage. Bandwidth? With 1 billion reads at 1 kilobyte each, that's roughly 1 terabyte of read bandwidth daily. These numbers highlight the need for efficient replication to minimize storage and bandwidth costs. Think about this. These estimations will directly impact our choice of replication strategy and infrastructure. We'll need to carefully consider the trade-offs between storage, bandwidth, and consistency. With a solid understanding of the requirements and scale, let's tackle the high-level design. We can use leader-follower, multi-leader, or leaderless replication. Leader-follower offers simplicity, with one leader accepting writes and replicating to followers. Multi-leader allows writes to multiple nodes, increasing availability but introducing conflict resolution complexity. Leaderless replication, like Cassandra, allows writes to any node, using quorums for consistency. We'll separate read and write paths to optimize for our read-heavy workload. The CAP theorem dictates we must choose between consistency, availability, and partition tolerance. For most use cases, we'll favor availability over strong consistency, opting for eventual consistency. We choose eventual consistency because it allows the system to remain operational even during network partitions, at the cost of potentially serving stale data temporarily. Remember the 1 billion transactions per second we mentioned earlier? This architecture is designed to handle that kind of scale. We'll expose a REST API, post/API/v1/transactions, account ID, amount, timestamp, returns transaction ID, status. We use an API gateway because it provides rate limiting and authentication, protecting our backend services. This brings us to a crucial challenge, maintaining consistency with leaderless replication. We use quorums. N equals total nodes, W equals write quorum, R equals read quorum. For strong consistency, R plus W greater than N. For eventual consistency, R plus W less than N. For example, with N equals 5, W equals 3, R equals 3, we have strong consistency. With N equals 5, W equals 2, R equals 2, we have eventual consistency. Conflict resolution is critical. Vector clocks track causality, helping resolve conflicting writes. The mistake most candidates make is ignoring network latency. High latency increases the probability of conflicts. Idempotency is also crucial. Operations should be safe to retry without unintended side effects. Your interviewer will push back. Why not just use strong consistency everywhere? The answer is that strong consistency significantly impacts availability and latency, especially in distributed systems. Eventual consistency provides better availability and performance, accepting the risk of occasional conflicts. We use vector clocks because they provide a mechanism for detecting and resolving conflicts in a distributed environment, unlike simple timestamps, which can be unreliable due to clock skew. Here's the twist. Even with eventual consistency, we can use techniques like hinted handoff to improve durability. Hinted handoff temporarily stores writes on a healthy node when another node is down, ensuring the write is eventually delivered when the node recovers.
Having locked down the core logic, let's consider the data model. We'll use Cassandra for our leaderless replication, given its high availability and scalability. We chose Cassandra because it's designed for high write throughput and fault tolerance, making it suitable for our use case. A sample schema. Create table users, user ID, UUID, primary key, username text, email text, created at timestamp, last login timestamp. We index username and email for faster queries. Data lineage tracking is crucial. We'll add job ID to track data transformations. We also need audit fields like created at and last login for monitoring and debugging.
That said, there's a hidden problem here: read-write amplification. With a 3x replication factor, each write becomes 3 writes. To mitigate this, we can use caching. Redis in front of Cassandra reduces read load, improving latency. Sharding distributes data across multiple clusters, further increasing scalability. Remember the 1 billion transactions per second Google handles? To handle that volume, we need horizontal scalability via sharding. We use consistent hashing for sharding because it minimizes data movement when nodes are added or removed. Your interviewer will probe: what happens during a network partition? With leaderless replication, the system remains available, but consistency might degrade temporarily. Read repair mechanisms ensure data eventually converges to a consistent state. We use Bloom filters to avoid unnecessary reads to Cassandra, improving overall read performance. We considered using a CDN, but the data isn't suitable for caching at the edge because it's highly dynamic and personalized.
The next piece of the puzzle is reliability. For fault tolerance, we deploy multiple Cassandra nodes per data center and multiple data centers per region. We monitor key metrics: write latency, read latency, and replication lag. We set up alerts for anomalies. For example, if write latency exceeds 100 milliseconds, we trigger an alert. We also monitor replication lag. If it exceeds 5 minutes, we investigate. Your interviewer might ask, what happens if an entire data center goes down? The system continues to operate with reduced capacity thanks to multi-data center replication. We use a heartbeat mechanism to detect failed nodes and automatically trigger failover procedures. We also need to monitor the payment gateway, ledger, transaction service, and fraud detection systems to ensure end-to-end reliability. We've designed a robust, scalable, and highly available replication system. The key trade-offs: leader-follower, simple, single point of failure; multi-leader, complex conflict resolution; leaderless, eventual consistency. Future steps: explore consensus algorithms like Raft for stronger consistency when needed. Remember, choosing the right replication strategy depends on your specific requirements and constraints. Now go build something amazing.
Get more system design breakdowns, coding patterns, and technical deep dives delivered straight to your feed. Hit subscribe and turn on notifications.